Very good morning to all. I just welcome you all for this session on nuclei, second presentation. Here I just concentrated on some of the old questions only and some of the detailed explanations over there. Just go to on this one. If you are having any doubt, you just mention the doubts and question number in the comment section so that I just try to explain this one in the comment only. If you are mentioning this one, I just put a separate chart so that you can understand. I just share that one. What are the doubts you are going to ask? I just make a separate slide as a chart so that I can put this one. I just share you. You can use that link to find out all the doubts of yours. And even in the description, I have mentioned what are the presentation has been given, what are the presentation has taken in this. I just mentioned in the description section. You just go through. The first problem of the session here is about this one. How much energy is required to separate a typical middle mass nucleus, that is about a tin, into a constituent nucleons. Constituent means that will be breakdown into a next immediate nucleons, and a mass of tin they have given, and a mass of proton they have given, and mass of neutron they have given. In this case, what they are asking here is energy, how much energy that is required. See, you can see this one, all are in million electron volt that can be required to separate tin to the constituent nucleus. See, for this one, I hope you know about this one general thing. What are the data has been given? I just write on here. This is about tin. Tin atomic number they are given, that is 50, and a mass number here is 120. And I just mentioned separately, atomic number here is 50 and the mass number A here is 120, and number of proton, how you can find out here, is A minus Z, that is 70 here. Now from this one, so the difference, see, energy required here is changing the mass, this one according to this formula, binding energy, we call it as a binding energy, that one, that is about a changing mass. And this one m into c square, even they have change given, this one here is 931.5 mega electron volt. This is the formula. In this case, we are going to find out the mass defect. Del m is nothing but mass defect. So mass defect formula here is del m is equal to Z, that is about atomic number into mass of proton, plus A minus Z into that is mass of neutron here, and this one minus of m, that is total mass of your tin. So this one, what you are going to find out here is the mass difference. Now this one atomic number here is 50 into mass of proton values they have given, that is 1 point. See, this one all maximum numerical values are plays an important role here, so that you just write down all the values over here, plus A minus Z here is 17 into, and they have given about mass of neutron here. Mass of neutron value here is 1.008 665, and this one minus of this one total mass of the tin values they have given, that is approximately 119.902199 unit. Now from this one, you just multiply here. See, 15 to 1.007, thus will become approximately 50 only, but numerical values are important one, so that you just concentrate here. See, maximum in this case, sum of the values will be very near. See here, this one to this 100 is there, and even this one to this one here is again the same 100 will be there, and even this one and this one here is 100 difference will be there. So little bit a difference only will be there, so that you just concentrate about this value. So once you are going to multiply this one, the value what you are getting here is 50.39125 plus 70 into this one, also the same 70 into 60.655 and minus 119.902199. Now you just add this one, all the numericals values. From this one, what you are getting here is 1.095601. That is atomic mass unit, that is about del m value. So once you got the del m value, now you just substitute here. What you are getting, that binding energy here is, now binding energy will be equal to, I just mentioned here, 1.095601 into 931, I just mentioned here, 931.5 mega electron volts. Once you are going to mention this one, what you are getting, that final answer here is 1021 mega electron volts. So answer in this case here is problem. This one also is similar like a previous problem, but here they have mentioned alpha particle. Previous one for the tin they have given atomic number and mass number and all. See here, calculate the binding energy of alpha particle. Given mass of proton here is 1.0073 unit, and the mass of neutron values they have given, and mass of alpha particle also they have given. From this one, first we are going to find out what is the mass defect. With the help of mass defect, we can easily find out what is the binding energy. For this one, first I just mentioned here what is the alpha particle. See, alpha particle you can mention here as this one 2He4. Helium we call it as an alpha particle. In this case, atomic number here is 2, and a mass number I just mentioned here, A is equal to 4, and number of neutrons, that is A minus Z, is equal to 4 minus 2, here is 2. See, from this one, how you can find out the mass defect here is del m will be equal to del m here is I just mentioned here Z atomic number into mass of proton plus A minus Z into mass of neutron. So mass of neutron here. Now 2 into mass of proton value they have given. Mass of proton value here is 1.0073 plus A minus Z, again that also 2 here. 2 into 1 point mass of neutron they have given 1.0087 minus, and the mass of helium, that last value you just see 0015. Now this is mainly important on the numerical values. So from this one value here is 2.0146 plus this one also the same 2.0174, and this value here is 4.0015. See, from this difference here is del m is equal to what you are getting, that value here is 0.0305 atomic mass unit. See, from this one binding energy, how you can calculate the binding energy? Binding energy will be equal to del m into 931.5 mega electron volt. Now I just mentioned a value over here, that is 0.0305 into 931.5, or even 931 is more than enough, we just mentioned here. From this one, what you are going to have here is 28.4 mega electron volt. So answer in this case, the next problem is on nuclear fission, fusion, and elementary particles. In case of radioactivity and some of the radioactivity decay and all, they have removed from the portions for EAMCET, as well as NEET also they have removed last year itself. This one, from this one, in this questions, what they are asked here is 200 mega electron volt energy is released when one nucleus of uranium undergoes a fission. When one nucleus of uranium is undergoes a fission, it will produce 200 mega electron volt. Find the number of fissions. Say number of fissions per second required. They have given the time here is per second required for producing 1 megawatt. 1 megawatt energy that can be produced, so that how many number of fissions is going to be happened. See, this one in case of power reactor, you can find out here the power output of nuclear reactor here is P is equal to Ne divided by T. See here, N is about number of fission taking place in a given time. Here is a 1 second they have asked here, so T is equal to 1. The number of fissions only we are going to find out here, and E is about energy released from fission. So what they are asking, the P value here is a total 1 megawatt of powers they are asking in this one. See, I just mentioned here for this energy for fission here is they are given here is 200 mega electron volt. Now 200 mega electron volt means 200 into mega here is 10 to the power 6. Electron volt in this case 1.6 into 10 power minus 19. So that one, if you multiply with this one, what you are going to have here is 32 into 10 to the power minus 12 joule. See here, this one 1.6 into 2, and this zero factor and all will go from here. E you got, then power here is, we have seen just now, Ne divided by T here, and number only we are going to find out N into E value, that we have found the value here is E is equal to 32 into 10 to the power minus 12 whole divided by time T here is 1 second. See, if that one will be equal to what they are given here is 1 megawatt. 1 mega means 1 into 10 to the power 6 watt. See, from this one I just mentioned here, from here N is equal to 1 into 10 to the power 6, again into T here is 1 value, and divided by 32 into 10 to the power minus 12. So from this one what you are having here is, you just cancel it from this one, 3 point, see from here what you are going to have here is 3.125 into 10 to the power 16. So answer is, problem, in each fission of uranium U-235, 200 megavolt of energy is released. See, for each fission, 200 mega electron volt energy is released, that is like a previous one, if the nuclear reactor produce 100 megawatts of power. Now, in this case, what they have given here is 100 megawatts of power is produced. Now, the rate of fission, in this case, what they are asking here is the rate of fission in this point. Now, see, previous one, similar concept, we are going to find out what is that energy. I just repeat again here. So, E is equal to the same concept. So, from this one, E here is, what they have given here is 200 mega electron volt, a similar concept. 200 into electron volt here is 1.6 into 10 power minus 19. See, from this one, what you are having here is 3 3.2 or even 32 into 10 power minus 12 joule. So this is about energy here. So E value they have given. From this P value I just find out here. So P is equal to Ne divided by T, and from this one P value already they mentioned here, that is 100 megawatts of power. 100 into megawatts here is 10 to the power 6 watts of power. That one will be equal to N into, already we found the value of E, 32 into 10 to the power minus 12 divided by T here is per minute. I just mentioned as 1 minute. But here what we are getting here is per minute. In this case 1 minute is equal to 60 seconds. See, from this one 1 second, those the time period here is 1 second. So I just mentioned here 1 divided by 60 minutes. What we got here is in a second. Now instead of this one we are going to mention in minutes. See, from this one for N is equal to, so this one here is 10 to the power 6 into 100. I can mention this one as 10 to the power 8 divided by 32 into 10 to the power minus 12. This is per second, right? Now you just need to convert this one. See, from here what you are getting, the previous one only answer, 3.125 into 10 to the power of 18 per second. Now per second in this case 1 divided by 1 second here is 1 by 60. Now you just mention here 3.125 into 10 to the power 18 by per second means divided by if you put 1 divided by 60, the 60 will come in a numerator, so 3.125. Now I just mentioned here 3.125 into 10 to the power 18 and into 60 here. So for this one what you are going to have here is N is equal to 1.9 into 10 to the power of 20 per minute. So this one 1 by 60 here is, see this one 1 by 60 here is minute. So this one answer in this case minute. So answer here is on a nuclear fission. See, in a nuclear fission, 0.1 percentage of mass is converted into an energy. Like Einstein mass energy equivalence, you can use this one. Mass has been converted into an energy. The energy released by the fission here is 1 kilogram of mass. So now this one, what you are getting that answer, see, according to Einstein mass energy equivalence, I just mentioned here, that is formula here is del E. That one will be equal to del M c square. This one, this is about a mass defect, or even this mass has been converted into an energy. Now this one from here, I just mentioned, I just going to find out what is del m. Del m here is 0.1 percentage. Percentage in that case 100. See this one, that is mass here is 0.1 percentage of mass. Now we are going to find out this one. See from here, zero point 0.1 we can mention like 1 divided by 10 whole divided by 100. So that is 1 divided by 1000. That is del m. So what you got here is del m you got here. Next one, del E. Del E here is already you found del M value here is 1 divided by 1000 into C square. C square here is 3 into 10 to the power 8 meter per second whole square here. Now, see what you are having here is 9 into 10 to the power 16 divided by 1000 here. 1000 here is 10 to the power 3. Now, 9 into 10 to the power of 13 joule. See what you are getting that answer in this case, that is in joule. What you are going to find out the answer also in joule from, but we are going to find out all the answer if it is in a joule means it's okay. You can easily directly get the answer. This is the answer for in case of joule, but they are asking the answer in case of kilowatts. See here 1 joule. This is important one. See remember here they haven't mentioned this one. You just need to convert here. 1 joule is equal to 2.78 into 10 to the power minus 7, that is kilowatts hour. Kilowatts hour. Now I just going to find out the value of this one in kilowatts hour, that is 9 into 10 to the power 13. Instead of 1 joule, I just going to mention as 2.78 into 10 to the power minus 7, that is in kilowatts hour. See if you multiply this one, what you are going to have here is 2.5 into 10 to the power of 9 kilowatts hour. Now you just multiply 9 into this one, you are going to find out 2.5. So 9 is approximately equal to 1. Now you just multiply with this one to this one, you are getting approximately 2.5. So answer in this case, this one. Calculate the energy released by fission of 2 gram. See here 2 gram of uranium in kilowatt. See first one, given that energy released per fission is 200 mega electron volt. Already we found the value here. Previous problem we can see that one 200 mega electron volt, how we have converted here. See in all the answers you can see this one, that is in kilowatt hour. See here this is 2 gram. Before and all we have seen about 1 gram of substance, how much energy has been released. Here they are mentioned as 2 gram of substance in this one. See here energy released in this case. See here the new energy released for 2 gram of substance, I just mentioned here E dash will be equal to this one. This is about 2 gram of substance, and here total how many amount of substance, how many grams of substance over here. This is from this one, and N into E. See this one, small m is about 2 gram of substance, capital M is about uranium U-235. So the total mass number into N is about Avogadro number. Avogadro number is about a number of moles, number of electrons are present over here, and number of molecules are present in 1 gram of substance here. From this one, E value already we found out, that is 200 mega electron volts. Now I just mentioned here 200 into mega electron volt here is 10 to the power 6, and the electron volt here is 1.6 into 10 to the power minus 19. That one, see here from this one, I just repeat the sentence here, 2 divided by 235 into Avogadro number you just mentioned as 6 into 6.023 into 10 to the power 23. Approximation I just mentioned here 6 into 10 power 23, and 200, this one already we found the value here is that is about 32 into 10 to the power of minus 12, that is in joule. So everything we have to convert this one in electron volt. Again I just mentioned here, 2 divided by 235 into 6 into 10 to the power 23, and this one 32 joule here is, see your you can mention here from this one, 1 joule is equal to, in the previous problem only we have seen from this one, here is the I just mentioned here, that is you can mention this one, 1 joule will be equal to 2.78 into 10 to the power minus 7 kilowatts hour. Now you just mention this value here, that is 32. See, already we found the value here, 32 into 10 to the power minus 12. In addition, instead of 1 joule, you just mentioned here 2.78 into 10 to the power minus 17. See this one, you just convert this value and this value, that almost approximate value, so that this one 235 here is, you can mention like um, 2.35 into 100. Right, now you can cancel over these two similar, almost similar value, like that you just try to cancel here from this one, 6 into 2 12 and into 32, or even um, uh, 32 into 2 64 into 6 216, like that you can mention here. From this one you can find out the answer, so you just cancel it. From this one you can get the answer will be approximately 4.54, and you can cancel this values over here. So 4.54 into 10 to the power 4 kilowatts hour. So answer in this case here is this one. They have asked in the previous year questions. An explosion of atom bomb release an energy. During explosion of bomb, they have released the energy of 7.6 into 10 power 13 joules. If 200 mega electron volt energy is released per fission. See this one we have find, and the previous also we got the answer 32 something, 13 to 10 to the power minus 12, like that we are getting the answer same one. See this is for one fission of uranium, how much we are getting that energy. For this one here is 200 mega electron volt. What they are asking, the number of uranium atom undergoes a fission. How many number of uranium atom which undergoes a fission, so that it will produce 7.6 into 10 power 13 joules, and a mass of uranium used in the bomb. That is how much quantity of uranium can be used to produce this one. See here in this case, I just mentioned here this one a number. How you can find out the number here is mm, this one I just mentioned here. N is equal to, N here is total energy divided by energy per fission. So this one energy per fission, so that you can find out total number of fissions. See here, this is for one fission and this is for total energy. This is one fission energy. In between these two, what you can get here is number of fission. Now you just substitute the value here. The total energy here is 7.6 into 10 to the power 13 joules, and divided by per fission energy here is 200 mega electron volt. Mega means 10 to the power 6, and the electron here is 1.6 into 10 to the power minus 19. Even that one also in joule, so that what you are getting, that answer here is 7.6 into 10 to the power 13 divided by this one here is 32 into similar one, 32 into 10 to the power minus 12. You always remember this answer. For 200 mega electron volt energy has been released in case of one fission of uranium. See from this one, if you solve it, what you are getting, that number of fission is going to happen here is 2.375 or even 2.38. Once you are going to solve this one, 2.38 into 10 to the power of 24. See here, this number of fission of uranium is going to happen. And next one, mass of uranium. What they are asking, the second question here is mass of uranium. See, there are two chances are there, whether this one will be the answer or this one will be the answer. And mass of uranium here is mass of uranium. How you are going to find out uranium mass here is, see, I just mentioned here, m is equal to, that is total mass number into number of fissions and whole divided by Avogadro number. So now if you mention here is 235, and number of fission is how much it has been happened here is 2.38 into 10 to the power 24 whole divided by, and this one Avogadro number here is 6.023 into 10 to the power 23. So this one I just mentioned here, so that if you cancel this one from this, you just cancel it for this one around 640, means 4 times will be there, around 40 times you can mention here, and from this one you just multiply here. What you are going to have here is 926.66 grams. So answer in this case here is this one. Last year questions they have asked this one. Consider hypothetical annihilation of a stationary electron with a stationary positron. See what you mean by annihilation in this case, the conversion of one particle or even matter into an energy by the mutual conversion between one particle into an antiparticle. See here is electron and positron which are going to convert, so the matter will be converted into an energy. So what is that wavelength of the resultant radiation? See in this case, now I just mentioned here for electron. See here what they have mentioned here is for one electron. So here is one electron I just mentioned as 1e0, and a positron here is plus 1 will be there, plus 1e0. That one will produce into one electron and positron combined together, that will produce a gamma radiation for each gamma wavelength. See for generally I just mentioned here conservation of momentum. Now I just mentioned here conservation of momentum into two identical particles. So into two identical particles, one is about only charge is going to vary. So this one, two identical particles. Now this one here, so it can be travel in opposite to the direction. So I just mentioned as both are travel in opposite to the direction. So that what happened here is, so both will be in opposite to the direction, but both are charges which is having equal magnitude and momentum also, which equal magnitude and momentum. So the energy in this case, what I'm going to mention here is for the law of conservation of energy. For the first one here is HC divided by lambda. See this one from here energy. So that what I'm going to mention here is, this is for one electron, and another one is for a positron here is HC divided by lambda. That one will be equal to, according to that energy here is m naught c square, and another one, both mass will be the same, only charge is going to change, so m naught c square. So what you are having here is, see from this one, this is 2 m naught c square, and this one also 2 hc divided by lambda, and this is 2 m naught c square. So 1 c will be cancelled here, and even a 2 and 2 will be cancelled here. See from this one, what you are going to find out, the lambda will be equal to, lambda will come to here, and this one will come to over here. So lambda will be equal to h divided by m naught into c. So answer in this case, previous chapter is over, and I forgot to tell the previous one. Don't don't think that one. How I mentioned here hc by lambda in this case. This one, yeah, E equal to h nu formula. Hope you remember. I just mentioned here. I couldn't go the previous section, so that I just mentioned here E is equal to h nu. From here, nu is frequency, so nu equal to c by lambda. So hc by lambda. This one I have mentioned directly. E is equal to hc by lambda. This is about the photon energy, and the Einstein mass energy equivalence equal to m naught c square. That's what I have mentioned in both the case. These steps I didn't tell you. Hope you to know about this one. So you just use this one. Up to this nuclear chapter will be over, and the next chapter will be on dual nature of radiation and matter. This is also this only one chapter. You are having two questions in case of EAMCET as well as NEET. You just concentrate over here. If you are having any doubt, you just pass your comments or your doubts on the comment section, so that I just mention this one. Okay, you just subscribe the channels, and if you are having any doubt, you just mention here and share it to your friends, those who are preparing for the NEET and the EAMCET examinations. Say almost similar problem, even a NEET and the EAMCET both are similar weightage of problems will be there. You just go through any doubt, you just mention here. I try to explain this one.